day, students. Today, let us discuss the matrix form to represent refraction of light. Let us consider a case where light is being refracted upon a surface. For that, assume this to be the z-axis. This is the axis along which light ray is propagating. In optics, we usually assign z-axis as the axis of propagation. Let us place a convex spherical surface S' upon the z-axis. This separates two different medias of refractive indices mu1 and mu2. Light from the first medium of refractive index mu1 is incident upon B of the spherical surface and refracts into the second medium mu2. Hence, the path followed by the light ray is A, B, C. Let us draw a normal at the point B. The normal passes through the center of curvature of the spherical mirror, and length BD is the radius of curvature of the spherical mirror. PQ is a line drawn adjacent to the z-axis, parallel to z-axis, and passing through point B. The angle made by the normal ND and z-axis is phi. Likewise, this will also be phi. The angle made by the normal and incident ray is I, and the angle made by the normal and refracted ray is angle of refraction R. The angle made by the incident ray with the z-axis is called alpha 1, and the angle made by the refracted ray with the z-axis is called alpha 2. Hence, I can write the relation I is equal to phi plus alpha 1, and angle of refraction R is equal to phi plus alpha 2. At the point of refraction, the distance of the ray from the z-axis is x. If the distance before refraction is x1 and the distance after refraction is x2, since refraction occurs at a point, I can write x1 is equal to x2. Now, according to Snell's law, mu1 sin I is equal to mu2 sin R. Since the angle of incidence and the angle of refraction is very small when we consider paraxial rays, I can approximate sin I as I and sin R as R. Thus, mu1 I is equal to mu2 R. Now, substituting for I and R in terms of phi and alpha, I can write mu1 into phi plus alpha 1 is equal to mu2 into phi plus alpha 2. I can write mu1 phi plus mu1 alpha 1 is equal to mu2 phi plus mu2 alpha 2. That is, mu2 alpha 2 is equal to mu1 alpha 1 minus mu1 minus mu2 into phi, or in other terms, mu2 alpha 2 is equal to mu1 alpha 1, there is a correction, this is plus, right? Mu1 alpha 1 plus mu1 minus mu2 into phi, or here I can take the negative term and write mu2 minus mu1 into phi. Here, from the arc shown here, I'm going to write the tan of phi. Tan phi can be written as x1 divided by r. Since phi again is very small, tan phi is approximated to phi. I get phi is approximately equal to x1 by r. Hence, replacing the term for phi, I write mu2 alpha 2 is equal to mu1 alpha 1 minus mu2 minus mu1 into x1 by r. Now, mu into alpha can be replaced in the term of optical direction cosine lambda. Thus, I'll be able to write lambda 2 is equal to lambda 1 minus mu2 minus mu1 by r into x1. Now the term mu2 minus mu1 by r is actually the power of the refracting surface. Hence this term can be further simplified as lambda 2 is equal to 1 into lambda 1 minus p into x1, where p is equal to mu2 minus mu1 by r, right? And let this be your first equation. Now, at the point of refraction, I have written x1 is equal to x2, or in terms, x2 is equal to 0 into lambda 1 plus 1 into x1, right? Let this be our second equation. Now to write this two equations in the matrix form, I take the two equations which were lambda 2 is equal to 1 into lambda 1 minus p into x1 and x2 is equal to 0 into lambda 1 plus 1 into x1. So I'm going to write the final refracted ray in column vector form lambda 2 x2 is equal to a matrix acting upon the incident ray lambda 1 x1 in column vector form. So in order to get this equation, I can write the terms 1 minus p, 0 and 1. So we get a 2 by 2 matrix of the form 1 minus p, 0, 1. And this is the refraction matrix, where p represents the power of the refracting surface. It is mathematically given by mu2 minus mu1 by r, where mu1 is the refractive index of the first medium, mu2 is the refractive index of the second medium, and r is the radius of curvature of the spherical surface. By property, determinant of R, matrix R, is equal to, yes, 1. If you take the determinant, you can see it is 1. That's all for today. Thank you.